everybody. In this video, we are going to be graphing the secant parent function. Since we're graphing the secant parent function and we just did the cosecant parent function, I think that we could kind of figure out what it is that we have to do. First thing we got to do is we need to recognize what is the reciprocal of secant. So cosine is the reciprocal of secant, and vice versa, of course. Make sure also, it might not be a bad idea to not abbreviate cosine as cos, because we're messing up and people are looking at the abbreviation for cosecant and they're saying cosine, and you don't want to do that, okay? So maybe, a little practice, full name when you see it. I feel like I get abbreviating tan, cotan, but cosine and cosecant, I might not, because you guys are kind of saying one thing when you mean another. So watch out for that. Now, if they're reciprocals, that means when cosine equals 0, remember, 0 or zeros is the name we used in algebra to describe x-intercepts, because that's where the y value was equal to 0. When cosine equals 0, secant, do you know what the answer to this rest of my sentence is undefined. Remember, they are reciprocals. Okay? Now, that means where cosine has an x-intercept, secant has a vertical asymptote. Now, obviously, we can shift the entire graph up or down. If we do that by using k as anything other than 0, our x-intercepts are now our sinusoidal axis intercepts. Okay? So wherever cosine would have crossed the sinusoidal axis, secant will have vertical asymptotes. Comprende? Wherever cosine would cross the sinusoidal axis, secant will have, spell everything correctly please, vertical asymptotes. The equation of a vertical line equation of vertical lines is x equals a number, all right? And I guess we could do a semicolon. Horizontal, and we've been doing this, so we should be aware, right? And horizontal lines is y equals a number. Probably could have done that a little better. Maybe I should, I have an idea, should just include a little bit of color coordinating, because then my purple highlighter fell down before. Sorry, pup. I was using purple, I believe, for my vertical asymptotes. Try to be consistent. I mean, if you had me as a teacher last year, or if you kind of just caught on to how I tend to do things, I hope you've invested in a pack of like highlighters or something. Crayons, I like to color coordinate. I try my best. Can't always do it as perfectly as I'd like, but we all do our best here. All right, so a couple little notes there. We wanted to label them. We're going to have, and I didn't say of a vertical asymptote specifically, just horizontal or vertical lines, because the sinusoidal axis is not an asymptote. A horizontal asymptote really is a line that we draw dashed. most dashed lines that you draw in your graph are there to guide you in the drawing process. But horizontal asymptotes specifically, you see them in things such as an exponential function or a rational function. Well, this is important because we're going to do limits later this year. And what they are describing to us is the end behavior. What is happening way, way, way at the ends when x gets bigger and bigger and bigger and bigger towards infinity? Where's my y value going? Is it also getting infinitely large? Is it also getting infinitely small towards negative infinity? Is it getting closer and closer to 0, which is different than getting closer and closer to negative infinity, which you can't really do. But they are different. So horizontal asymptotes, they're sort of there as like that magnetic force that might be pulling our graph towards it in one direction or another. It could be linear, horizontal line. It could be a line with a positive slope or a negative slope. You could even have horizontal asymptotes in the shape of a polynomial. Your end behavior could be modeled by a quadratic or a cubic and so on. So lots of possibilities, and that will be guiding us for our limits at positive infinity and at negative infinity when we do limits later on. Vertical asymptotes are involved with limits as well. Vertical asymptotes are more often than not very, very strict. You cannot cross them. All right, it is identifying more often than not. Again, I'm saying that because, you know, you might be dealing with a different type of graph that's not necessarily a function, whatever. But you have a vertical asymptote. Think of that as somewhere you cannot cross. It will not include anything for your domain at all. And that usually comes from when your function is undefined. So they're both asymptotes. They're both dotted lines. They both guide us in drawing our graph, but they result from different things. Okay? But we'll chat more about that in the future. I just want to plant the seed, you know? Now, before we graph secant, we should graph cosine, but dashed. I guess what we could do this time is, because it's a little awkward looking, and you guys do a lot of funny things when you draw your secant graphs, I'm going to actually draw 2 cycles. I'm going to draw the period from 0 to 2 pi, and I'm going to draw from negative 2 pi to 0 as well. But I'll start here, I'll draw secant, and then I'll tack more on in front of it so you could see the fuller picture of a little bit more of the graph, okay? So straight across, since it's the parent function, we have a k value of 0, we have an h value of 0, we have an a and a b value of 1. So y equals, I'm going to write 2 things here, a secant, b x minus h plus k, and underneath that 1 secant 1 x minus 0 and plus 0. Okay? I hate that I squash things for you guys, but you know, that's life, I suppose. I'll color it to make it a little bit better. Not great. Forgive me. Okay, so let's get going. I like to try to make it nicely spaced, you know that. So if this right here is 2 pi, right in the middle, I will have pi. What's it halfway between? This is going to be then pi over 2, 3 pi over 2. Keep in mind a little note for yourself if you ever try to make this to scale, which I don't suggest because that's a little nutty. Pi over 2, pi, 3 pi over 2, and 2 pi. What are these numbers? Well, let's even do this. What are these numbers as decimals? Because if you did try to use graph paper and to make it to scale, well, pi is 3.14, approximately. That means half of pi, which is pi over 2, 1.57. 3 pi over 2, well, it's really the sum of both those, pi over 2 and 2 pi over 2 equals 3 pi over 2. That is going to be about 4.71, and 2 pi is approximately 6.28. So think about that if you ever are using graph paper and trying to make things to scale. I mean, if that's 1 unit, then that's about half a unit. It's a little bit stretched out, but this is also why we call it the rectangular coordinate system, not the square coordinate system. You know, your boxes on one axis and your boxes on the other axis, they don't have to be the same. Even though you might be using squared graph paper as your grid, it doesn't mean it really represents a square. All right. Anyway, continuing. While it's not necessary, this would be, you don't have to copy this part down, pi over 4. That's 45 degrees, right? Then that would have been 15 and 30, right? 30. Then that would be 45, 60, 75, and 90, okay? So I just drew tick marks every pi over 12 radians or 15 degrees. I'm just going to save that for a minute because I know it was a little awkward with talking about the 1/2 and the 2, and I want to do it more for real this time. So we'll see that in a moment. Okay, cosine. Going around that unit circle, all right? Cosine at 0. Input, x-axis. X is right here. That's the input or the angle that we're filling in. Y, output on this axis. What's the answer, right? What's the cosine of 0? It's 1. All right, plot the 1. What's the cosine of pi over 2? The top of the unit circle, the x value is 0. What is the cosine of pi? -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is also 1. If you are confused a bit, press pause, bust out your unit circle, and look it over because you can't just let yourself be confused, okay? Watch out for that concavity when you draw this. Try not to make it too pointy. Lovely. There we go, okay? Now, I drew it dashed because it's not really here, okay? Make believe. Everywhere that cosine is 0, secant is undefined. We got an asymptote right there. And you got an asymptote right there. Our sinusoidal axis is wherever k is, and at this moment it is on the x-axis. And always remember, the equation of the x-axis is really just the line y equals 0, and the equation of the y-axis is really the equation of the line is x equals 0. All right, next. Finding those reciprocals. So cosine has a maximum value right over here of 1 at 0. What is the reciprocal of 1? The reciprocal of 1 is 1. No, it's not -1, it's just 1. So that point right there, it's a keeper. So is this one right over there, and the same idea with -1. Those 3 points are the only points in this area that are on both sine and, I keep saying sine, are both on cosine and secant, all right? Now let's take a minute and talk about these extra tick marks I threw in. Where is pi over 3? Pi over 3 is right about there. What is the cosine of pi over 3? The cosine of pi over 3 is 1/2. If that's 1, then that's 1/2. So really, it should be going through about that dot right over there. Now, what's the reciprocal of 1/2? The reciprocal of 1/2 is 2. So while cosine passes through 1/2, secant, on the other hand, is going to pass through the point pi over 3, 2. If we were to go a little lower, and I don't know exactly what angle it would be, but if I were looking for about 1/3, cosine is 1/3 right about here. If cosine is a third right there, then secant would be what? 3. What about half of a half? Right about here, looks like cosine's 1/4 of the way up. If cosine is 1/4 of the way up, what is secant going to be? 4 units up. So as this concept is important, excuse me, as cosine, the output values of cosine approach 0, and they get smaller and smaller and smaller. I don't want to get to 0, so I say approach because I can't get there because secant can't get there, all right? But as cosine gets closer and closer to 0, what is secant going to do? Think about what happens when numbers get closer to 0. Use the fractions like 1/10, 1/100, 1/1000, 1/10,000, 100,000, and so on. As these get smaller and smaller and smaller, or a fraction's denominator grows bigger and bigger and bigger, the reciprocal, flip it, the reciprocal as a whole gets bigger. Denominator's getting bigger, make a number smaller. Numerator's getting bigger, make a number bigger. So this is just going to go up, up, and away. Same concept here. That's about there. So here-ish is going to be my other pi/3 angle, right? Somewhere in this general area. -1/2 would be right about there. So secant would be -2. Same idea on this side, right? So on and so forth. I'm not going to go crazy. Just remember it has a very similar graph to cosecant. It's co-function. And to cosine, it's reciprocal. And then this piece right over here is going to go up like that. Now, maybe if you graphed and followed along and did it with me, you were okay. However, when you guys draw this on your own, I don't know what happens to this little piece. Weird things. So really, really take your time and remember that all you're seeing is half and half of one of these little U shapes right over there. Okay? So another concept, reciprocals, that flipping, that maximum, minimum, big, small idea. So when cosine is at its biggest value, that's secant's smallest. As cosine is at its smallest value, that's locally secant's biggest. Okay? It's like one man's trash is another man's treasure, right? So that looks okay. And then here, what I wanted to show you is like how it's half of it. So this is one cycle. If I cut this out and made a little stamper out of it, and I was like, okay, stamp, 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 one after the other, right? Or I made tiles, right? And I put another tile, and another tile, right? So I'm not going to be as, actually, I mean, I did put that tick mark. I could go kind of in the middle. So these over here are just the negative. So this is us going from 0 radians. Sorry if you hear my dog snoring on my lap. There it goes again. That was us going this way from 0 to 2 pi. And now this piece is going to be us going this way from 0 to -2 pi. Okay? So this is -pi/2. This is -pi, -3 pi/2, and -2 pi. Also, another reason I'm showing you this is because sometimes if you ever have like a matching multiple choice test or something like that where you have to like analyze a graph, they may show you 2 full cycles instead of 1. So, you know, how do you make sure you read that correctly? Make sure you're experienced with that. I just want to make sure you see. So -pi/2 is coterminal -pi/2 with 3 pi/2. So whatever happens at 3 pi/2 should be happening at -pi/2. -3 pi/2 is coterminal with pi/2. So whatever happens at pi/2 should also happen at 3 pi/2. Could you still continue your little cosine wave? Absolutely. I'm a big fan of drawing the dashed cosine wave underneath. I think it's important. And then from there, a little flipperoo. Reciprocal or reciprocal. Be careful that like you don't flip this in a sense that like, I don't know, it goes anywhere between -1 and 1, that should be barren. Like if I were driving a car, it would be a smooth sailing through there. The only thing is a dotted line, which isn't really there. This would be wide open, okay? Because the way cosine oscillates between -1 and 1, secant is just like going right up against the -1 and the 1 and never ever goes in there, okay? There we go. We got this little U shape again. Remember we said they're not parabolas. And, you know, there we go. So when you have these little pieces, remember when you draw them, people tend to like flap them and curve them. The concavity is all wonky and weird. So just make sure you remember it is half of one of these little U-shaped guys. So if you picture the other half of it, I feel like you'll less likely mess up how you kind of put that together. And that right there is the secant parent function. And every other transformation that we are going to do is exactly as we did for sine, for cosine, and for cosecant. And I hope you were able to follow along. Again, we'll do domain and range in a separate video, but I hope you move on to either the domain range video for this one or you move on to the guided example. If you are down with this and you feel like, yeah, I'm getting it, makes sense, thumbs up. If you're like, still no idea, you're crazy, put a thumbs down. It's anonymous. I won't be insulted. I'm just trying to help you out. So go ahead. Ooh, those decimals, don't forget them. Important. So I will see you next time. Have a good day.